first, some words about myself. So my name is Nico. I am a front-end developer. I live and work in Switzerland. I'm also part of the Google Developer Experts program, and that basically means that I spend a lot of my free time just playing around with all kinds of new browser technologies, web technologies, and everything that's happening in the on-device AI space in the end. But let's start with a very simple question. So who is K.I.T.T? So K.I.T.T is short for Knight Industries 2000s. It's this advanced AI-powered car from the TV series Knight Rider. And the whole show is about Michael Knight and K.I.T.T, and they solve cases. So it's this good guys versus bad guys. So in the end, K.I.T.T is just this supercomputer, sophisticated AI. It's some sort of a person, but it's a car. So maybe we should rephrase the question. What is K.I.T.T? And in the 1980s, it was super simple. K.I.T.T is just a very advanced computer doing very advanced computer stuff. Simple. But then we learned about machine learning. So we have artificial neural networks. We have networks with neurons that are connected to each other, and they have weights between them. And if you tweak the weights, they will learn. So maybe K.I.T.T is just a huge artificial neural network. But in the age of AI, I have a simpler explanation. So maybe K.I.T.T is just an AI agent that connects different services with a decision-making process. Sounds reasonable? Let's build it. And if we want to build that, we first need to look into the features. What are the features that make K.I.T.T human-like? First of all, it listens and it talks. So we can talk to the car in natural language and it will talk back to us. It is intelligent, so it can process information. It's not just a soulless machine. It actually has humor. It has personality. It has a history. So there's series of, there's episodes of history between Michael Knight and K.I.T.T. And last but not least, it's not just a virtual application. It has a body. It exists in the physical world. Now, to build all of those things, we need a lot of machine learning. And I wanted to build everything in the browser. So how can we do machine learning in the browser? If you have been in Maxim's talk, in the previous talk, we did learn that, yes, we can use machine learning in the browser, but we need three things. We need hardware, and we need access to that hardware. We need libraries that interact with the models, and we need the models themselves. So let's have a look at the first part, the hardware. We can actually run machine learning operations in the browser. We can do that using WebAssembly or JavaScript on the CPU, which works, but it's quite slow. We can use the GPU, which is faster, using WebGL or WebGPU, or we can even use WebNN, where the operating system basically decides if it needs to use the CPU, GPU, or the NPU. If we talk about libraries, there's one library that Maxim also talked about a little bit, and that is Transformers.js. And Transformers.js was released in 2021 by Joshua Lochner, who is better known by his handle Nova. He then joined Hugging Face, so the whole project is now part of the Hugging Face family. And it was designed to be pretty close to the Transformers Python library, and it also stands on the shoulder of this open neural network exchange standard. So they are using the Onyx runtime web to run the models. And to use it, we can basically import this pipeline operator from Transformers.js. We can then create a pipeline using a task that we want to use and the model. There's a list of tasks and models on Hugging Face. And when this code runs, it will download the model and put that to the application storage, cache storage. So we can show the progress callback. There's also an option to decide whether we want to use the GPU or the CPU. And we can also define what compression type we want to use for our model. And once we have the pipeline, we can basically pass anything to the pipeline. It will then take the input, run that through the model, and it will then return the output. And the input and output types, they heavily depend on the task and the model that we use. So how can we use Transformers.js to solve our first problem? We wanted to have this listening and talking capabilities. So there is a model that we can use for transcribing spoken words, and that is Whisper. Whisper was trained and then open sourced by OpenAI, and we can use Whisper with Transformers.js So we can use the automatic speech recognition task with the Whisper Tiny, and we can then pass any audio to the transcriber, and it will turn the text as string. Pretty simple. On the other end, we can use Kokoro. And Kokoro is a quite new model, and there is Kokoro.js, and Kokoro.js was written by Senova, so it's a small abstraction layer on top of Transformers.js. And the way we can use it is pretty similar to Transformers.js. So we can have this text-to-speech pipeline that we can use the generate method to pass in any string, and we define the voice, and it will just work. So enough about the theory. Let's see how that works. I have this little pipeline here. I can just record anything. It will transcribe it, synthesize it, and it will then use the audio output. So I can, for example, say, "Hi everyone, it's pretty cool to be here at JSday in Bologna."
Hi everyone, it's pretty cool to be here at JSA in Bologna.
Okay, so we have an end-to-end pipeline that we can talk to. But there's one problem. It's not actually intelligent. So how can we add intelligence to the pipeline? The closest thing we have to intelligence right now is LLM. So we have large language models, so we can have a prompt as an input, and it will generate text for us. There's a huge list of LLMs that we can use, and they differentiate in the size and also in the open versus closed category. So the size is usually defined by the amount of parameters, the amount of weights that we have between the neurons. So it's also an indicator of how many neurons we have in the artificial neural network. And there are big ones like the GPT-4 with 1.76 trillion estimated parameters. But there are also smaller ones like the Gemini Nano with only 3.2 billion parameters. And the cool thing about that is the bigger the model, the more processing power we need to actually run the LLM. And for the big ones, we need entire racks of GPUs in some server farms. But for those smaller ones, we can actually use them on our device, on our laptop or on our mobile device. Now, there is closed models. That means that they were trained and then used by OpenAI or Google or whatever, and they maybe provide an API. We can use them there, but we cannot use them in our own system. But there are also open LLMs. And open means that the trained weights and also the architecture is open source, so we can actually use them on our own devices. And there's a whole category of small open LLMs like the Gemma 2 family. There's also Gemma 3 that was released a couple of weeks ago by Google. So those are models that are small enough to be used on device and that we can actually, or that we are allowed to use because they're open. And with access to the GPU using WebGPU, we can run them in the browser. There's one project called WebLLM, and with WebLLM, we can create an engine where we define the ID of the model that we want to use. Then we can create a conversation where we first have the system prompt, which basically sets the scene. It's the first prompt that the AI sees or the LLM sees, and then we have the user query. And then we can either wait for the full reply, or we can use streaming, so it will output the tokens once they are generated. Let's try that out. I have a little demo here. So we can, for example, say, who are you? And it will then generate the text. I'm Gemma, an AI assistant created by blah, 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 blah. And what we can see is that it's actually quite fast. And everything you see happens on my device. And it can process the input tokens at 70 tokens per second. And to then generate the output tokens, it does that at 31 tokens per second. And everything happens offline on device in the browser. So let's add that to our pipeline. Let's try that. Hey there, my name is Nico. I'm right now at JSday in Bologna. It's an amazing conference, and we are on stage right now. So could you quickly introduce yourself to the audience?
Hello, nice to meet you, Nico. I'm Gemma, an AI assistant, here to help make your JSday conference a smooth and engaging experience. Let's hear it for JSday, smiling face with smiling eyes.
Okay, we have a pipeline that we can actually talk to. But what we generated is just another random chatbot because I did not want to chat with Gemma. I wanted to talk to K.I.T.T. So how can I now customize the LLM? The first idea was to just fine-tune LLM. So we have all the conversations from K.I.T.T and Michael Knight. So maybe we could use that to fine-tune an existing LLM, but that is way too complex. I'm a front-end developer. I want to see what is possible in the browser. And there is another method that is way simpler, but yet very powerful, and that's just prompt engineering. And prompt engineering is the process of crafting precise and effective input prompts to optimize the output of AI models. What does that mean? I have the same pipeline as before, but now I have a different system prompt. And here in the system prompt, I say, hey, you are K.I.T.T from Knight Rider, speaking car that talks with Nico, so I give it some context. I also have some guardrails, keep your answers short. I then have a full summary of K.I.T.'s tone, so I can tell the LLM exactly how it should sound, how it should behave. And then I have more guardrails because I don't want to have all these symbols and emoji stuff. And that's the exact same pipeline, but with a different system prompt. Hey there, we are right now at JSday in Bologna, and we are on stage right now. So could you quickly introduce yourself to the audience?
Greetings, my designation is K.I.T.T, a sophisticated automotive computer and co-host of this evening's showcase.
Okay, and that's the exact same model that we used before, just with a different system prompt, and the output is very, very different. So let's talk about memories, because if we interact with people, it's a lot about things that we experienced in the past together or alone. And in the case of K.I.T.T, we actually have a lot of things that we can talk about. We have 4 seasons of just stuff that happened to K.I.T. And my idea was, how could I use all of that information in my pipeline? So the next few slides, they opened up a huge rabbit hole, but I tried to keep it as short as possible. But if you ever find yourself in the same situation, you might want to go to Reddit because you will find a subreddit of your favorite show, and there will be someone who has a link to a website with all the screenplays of your favorite show. You will then write a little playwright script that scrapes all the screenplays in plain text. Then you will find out that those screenplays are written in pre-World Wide Web times, so you need to write your own parser that parses the plain text into structured JSON, and now you have your database. So I have now 6,275 scenes in 432 acts in 84 episodes that I was able to then save to my IndexedDB, which is a document database that lives in the browser. But now I have a new problem. Let's imagine I have a question about something that happened in the past. So how does my bot, pipeline, or whatever, know what scene I am referring to? I mean, I could write just database queries, where I look for certain words, and if the word appears in the entry, that would be a match. That could work, but it's not very reliable. A better way is to use something called similarity search, also known as vector search. Who here has heard about vector search? Great. So what is vector search? Let's imagine we have 3 animals. We have a penguin, we have a kudu, and we have a giraffe. And we want to know how similar is the kudu to the penguin and to the giraffe. So first of all, whenever we want to calculate similarity, we need numbers. And we can turn our animals into vector representations. And a vector representation is basically just an array of vectors, an array of numbers. And what we can see here is that my vector representation is just the height, leg count, comfort temperature, weight, life expectancy. For the penguin, that means it's 1 meter high, it has 2 legs. The kudu is 1.7 meters high, has 4 legs, and so on and so forth. So once I have my vector representation, I can then use the cosine similarity algorithm to find distance between 2 points in this multidimensional vector space. And we now see that the kudu and the penguin have a similarity of 0.85, and the kudu and the giraffe have a similarity between 0.98. So it's way more similar to the giraffe than to the penguin. In other words, similarity search means that everything that can be represented as a vector can be compared for similarity. That makes sense for animals because we have those obvious vectors, leg count, life expectancy, and so on and so forth. But what about text? If we work with text, we need machine learning models again. And here I'm using a category of feature extraction models. And here I'm using the all mini LM L6 V2, and that is a machine learning model that was trained on semantic similarity. So I can create this extractor, and I can then pass any text to this extractor, and it will return an array of 384 numbers. Doesn't matter how long the text is, it will just return an array of 384 numbers that represent my text. Let's see how that could look. I have a text, hello people from the capital of Italy, and I have my vector representation. I also have another text, good afternoon developers from Bologna, and I have another vector representation. Now we see that we have a similarity of 0.64. We have very few shared words, so from is the only shared word between those two, but we have words with similar meanings. So hello people and good afternoon developers have a similar meaning. Now we also see that Bologna and Italy have a similar meaning, but if I change Bologna to Rome, we see that the similarity is higher. The similarity is now 0.74. So capital of Italy and Rome is more similar than capital of Italy and Bologna. Now, we have this database of all the scenes, and we want to find a way to search for similar strings. So how could I convert my scenes? And those scenes could be multiple conversations long, multiple plot twists, or they could be just one-liner. How can I convert them in a form that I can then use for similarity search? And the solution I came up with is to create this LLM summarizer. So the LLM summarizer is just a function that accepts the scene as text, and I will then just calculate how many summaries do I expect. In that case, for longer scenes, it could be 4 or 5 summaries. For short text, it could be just 1 summary. And then I have my LLM with a system prompt and with a user prompt. And in the user prompt, I'm very strict about what I expect. Find the main plot lines, maximum of max plots. And then I am also very strict about the output format, because I want to have a JSON array of all the summaries. Now, I have my LLM summarizer, and I was able to summarize all my scenes. And to do that, my poor little MacBook had to process 3.1 million input tokens to then generate 303,000 output tokens. And it took a couple of days. It also crashed sometimes, but I had my database with all the scenes with their vector representation. And that also means that I was able to create a vector search function. And what this function does is it accepts a query, just a question. It will then generate the vector embedding for the question. It will then go through the database. It will find the entries or it will calculate the cosine similarity between the query and the summary, and it will return the 4 scenes with the highest similarity score. Pretty simple. Now, how can I use this vector search function in my pipeline? And that's a concept called function calling. A couple of important things about function calling. First of all, an LLM does not execute a function. The application around it can. The LLM only detects when a function should be called. It will then generate structured output, could be text, XML, or JSON, and the application can then use the structured output to call the function to return the return value to the LLM, and they will then process that in the next step. You could use frameworks for that, but a big part of my side project is that I wanted to see how stuff works under the hood. So I wanted to try that with pure text in, text out. So what I have is my maybe call function, and there I have a system prompt where first of all, you are a kid from Night Rider, blah, blah, blah. And then if you want to, you can use this function call find memories, and that's an XML snippet with the name of the function and with the query. I then provide some instructions, some examples, and my query. What I basically created is called a RAG system, and RAG stands for Retrieval-Augmented Generation. That means we generate an answer, but we first have a retrieval step where we augment our prompt with more information. To be more precise, I created an agentic RAG system because in that case, the LLM decides if it needs more information or maybe it does not. And if you're talking about buzzwords, that's basically what an AI agent does. It's a program that autonomously completes tasks or makes decisions based on data. Okay, let's try that out. I can now go to kit.nico.dev. I can now wake it up. And I can, for example, ask, good morning, Kit. How are you today?
Good morning, Nico. I am operational and ready for whatever task you have for me.
Okay, we can talk to Kit, but we can do way more than that. Let's imagine we have an actual question. Hey, Kit, do you remember the connection between Sonny and the deadly poison gas exchange, and did something tragic happen back then? By the way, I'm using just the space bar to record it.
While I don't have specific details about a poison gas exchange connection with Sony, I can recall a scene where Kit and Michael were involved in a situation with a dangerous chemical. It's possible this is what you're referring to. Yes, I do. In Season 3, Episode 8, a deadly poison gas exchange between Sonny and Fidel was observed. A bystander was killed when a canister was accidentally discharged. This tragic incident is a significant part of the show's narrative.
Okay, so what happens here? I have a system prompt, and the system prompt is quite big. So I have like, hey, you're a Kit for Knight Rider. I have, again, summary of Kit's tone. And then I say, hey, you have a list of tools that you can use. One of those tools is the search episode tool. We have the search episode with some arguments, with the examples that, I mean, LLMs love examples. If they see an example, they will just know what to do next. And then I have my question. And now what you can see is that it knows, hey, I want to call this a search episode function. So it has the function called XML snippet, and then it has some context so it can tell me something. My application can parse this response, and it sees, okay, there is this function. I should call this function. It will then call the function. It will return the return value of that function to the conversation. So now we have all the things it found in the database as more context. And now it can generate a new answer with this new context that I provided. One important or one funny thing is you can see that it tries to call this function twice. And that's a problem with small LLMs like the Gemma 2. It's a 2 billion parameter model. It's quite fast, but it's not very accurate. And I told it multiple times in the system prompt that if it already has the information to answer the question, do not try to call the function again. But it just does what it wants to do. So I had to be a little bit creative in my application. So if I already called the function, it shouldn't call the same function again. So there it knows, oh, okay, now I'm done. I don't need to call that again. So that was maybe the first part. But I also wanted to give, or I wanted it to have a body. I wanted it to live in or to exist in the physical world. And Kit is a Pontiac Firebird. I looked at some Pontiac Firebirds and they are at least 20,000 Swiss francs, and believe it or not, that's not in my side project budget. And also I'm not a mechanic, so even if I had one, I had no idea how to deal with that. But I'm still a kid at heart, so I was able to create a little Lego kit. So now I have my car and I have the web application. And how can I communicate with the car using the web application? And there is a great API that we can use for that called WebBluetooth. And WebBluetooth allows us to communicate with Bluetooth Low Energy BLE devices using or from the browser. And my car, in the end, it's an Arduino Nano RP2040. It's an Arduino microcontroller board. It also has a Bluetooth chip already on the board. It is connected to this little LED strip. Oh, I broke something. It's fine. It's connected to this LED strip and to the wheels. And on the Arduino, I have a very little C++ program where I have one BLE service that has one, BLE server that has one BLE service. And that service has one characteristic. that characteristic can have two values. One value controls the left side, one value controls the right side. So when I change the value of the characteristic, it changes the speed of the wheels. On the software side, it's pretty simple. I can use WebBluetooth to connect to the car, to connect to the service, to connect to the characteristic, and then I can get the value using characteristic.readValue, and I can change the value using characteristic.writeValue with a new value for the left and the right side. Okay, let's try. Let's go back to K.I.T.T, and I can now turn it on. So it's blinking, so it's now looking for a connection. I can now connect to my car. And now I am able to use arrow keys to control that. Okay, so I can do that using arrow keys, and I could now spend the last 10 minutes just cruising around with my car, but that's not the point of my project. So what I actually wanted to do is I wanted to integrate my car in this LLM pipeline. So let's try. Hey K.I.T.T, I think we need to get out of here. Just go full speed forward.
Let's get out of here. I've increased the speed to 100%. Let's make a break for it.
Okay. Just for the record, I have a little timer, so whenever it changes the speed to some value, it will do that for 2 seconds and it will then stop because I didn't want it to crash into the wall. But I can also do way more complex stuff than that, because I could also just write a little program that looks for full speed forward and will do that. That would be simple. But I wanted to have some actual intelligence in that little car. So what if we have a more complex query? Let's try, for example, hey K.I.T.T, we have a huge problem. There's a roadblock in front of us, and on the right-hand side, there is a river, so we can't go right either. What should we do next?
We'll need to make a left turn to find an alternate route. Let's go left.
Okay, so it actually tries to reason about the thing that I told it to do and tries to find the best solution using all the tools that I provided. So to sum it up, we were actually able to create K.I.T.T. It listens and talks using Whisper and Kokoro with Transformers.js. It is intelligent using the Gemma 2 LLM. It has personality using just plain prompt engineering. It has a history using all the scenes from Knight Rider and Agentic RAG. And last but not least, it has a body using WebBluetooth and function calling. Now, you know what I built, you know how I built it, but the real question is why? Why should anyone spend hours building a car or trying to rebuild a car from a TV series that I didn't even watch when I was a kid? And the reason is pretty simple. I learned programming because I wanted to build stuff. I did not go to university, so I tried just building websites for my band, for my colleagues, for myself in the end. And I was always fascinated by all the things that we can do with the web platform. So for me, it has always been just fascinating to see what we can build with the web platform. And as you have seen, there's so many things we can use. We have WebBluetooth, but we have so many APIs, WebUSB, we have WebAudio. There's so many APIs that we have in the browser. They're just there ready to use. And if you can just put it on some server, people are able to access it, people are able to try it, people are able to see what you've built. And I think that's amazing. And now with LLMs, we just have a new building block. We have a new thing that we can put in our application, and we can just use that. And that's pretty cool. So that was it from my side. Thank you so much for your attention. Yeah. My slides are there behind the QR code. The questions, there's the QR code there as well. I will be here for the rest of the conference, so if you have any questions, I love to talk about all those things. And I'm also trying to be as active as possible on LinkedIn and Blue Sky. And if there are questions, I think we do have time for some.